defined simple harmonic motion. We defined it as motion in which the restoring force is proportional to the displacement. Now, that doesn't make a lot of sense to us on the surface. Motion in which the restoring force is proportional to the displacement. But when we start thinking about that, like as we went through that lesson yesterday, it makes a little bit more sense, right? As you get further away from that fixed position, that equilibrium position we sometimes call it, the force becomes bigger. That's what causes the object on the end of a spring, let's say, to be pulled back toward that fixed point and to end up going through motion that repeats itself, right? If this is my fixed point and the spring is stretched beyond this fixed point, there's a force that pulls it back. And as it goes back, it speeds up, but the force decreases. And then as it goes through that fixed point, there's a force that pulls it back again. So that means that the object on the end of that spring ends up going back and forth, back and forth, back and forth. And that's what we perceive as simple harmonic motion. So because the force that pulls it back to the fixed point is proportional to how far the object on the end of the spring is away from the fixed point, we get repetitive motion. And that's what we define simple harmonic motion as. Yesterday we went through two equations, F is equal to negative kx for the restoring force, and then T is equal to 2 pi square root m over k. We went through this on our worksheet that we went over just a minute ago. Right? My two equations that describe fundamentally simple harmonic motion. Today what I want to do is describe simple harmonic motion a little bit more, but this time in terms of energy. Of course, there's two types of energy, just like there was back in our Unit 2, dynamics unit, kinetic and potential energy. Kinetic energy is energy of motion. And it doesn't matter whether you're talking about a car going down a hill or a grandfather clock pendulum vibrating back and forth, or an electron orbiting around a nucleus, or an Earth revolving around the sun. It doesn't matter. The kinetic energy of any object is equal to 1/2 kx squared. And that includes the object on the end of the spring vibrating back and forth. Its kinetic energy is 1/2 mv squared. The potential energy, on the other hand, there's many different kinds of potential or stored energy. If it's the car at the top of a hill, its potential energy is mgh. If it's an object on the end of a spring that's stretched or compressed, its potential energy is, and this is a new equation for you, 1/2 kx squared. Sorry, that first one should be 1/2 mv squared, right? 1/2 mv squared, and the second one for potential energy should be 1/2 kx squared. K being the spring constant in newtons per meter. Sometimes we would call it an elastic constant if we're doing this for an elastic, same equation. X would be the displacement. Not the displacement, how far does it move across the room, but the displacement, how much it's stretched by, or how much it's squished by. You know intuitively, if you take an elastic, you guys have done this, right? You take an elastic, put it on the end of your finger and stretch it, and you go to fling it at somebody. You know intuitively, even when you were a little kid, 6 years old, when you took that elastic and put it on the end of your finger and stretched it, you knew that if you wanted it to go faster, you needed to stretch it more, right? So even if you didn't know anything about potential energy, which I'm betting you didn't when you were 6, you did at some level, even though you didn't realize it, know about potential energy. You knew at some level that if you stretched it more, the kinetic energy would be more when you let it go. And the only reason that would happen is because you're giving it more potential energy. The more you stretch it, the bigger the value of X is, the more potential energy it has, the more potential it has to move faster. And you also knew at some level that the elastic that you stretched mattered as well. Some elastics would work better than others. In other words, it wasn't just how much you stretched it, but it was also the nature of the elastic. In other words, we wouldn't have called it this when we were 6 years old, but the spring constant, or the elastic constant of that elastic, or the spring. Yep?
Given how similar the variables are in
Yep.
the equation for potential energy and for restorative force, is there any way to directly relate those two?
Yes. The question is, given how similar the equation for force is, F is equal to K times X or negative K times X, and EP is equal to 1/2 KX squared, is there any way to relate those two together? The answer is yes. Okay? You don't have to know this, but I'll answer the question, okay? We defined 2 units ago, we defined work, let's put those away. We defined work as the change in energy, right? Work is the change in energy. So if we stretch an elastic, the change in energy would be delta E potential. It would be 1/2 KX squared. So let's say work is 1/2 KX squared when we stretch an elastic, we stretch a square. Good? Now, work is also equal to F times D. But the D here, when we stretch an elastic, would be X, right? So the work is equal to F times X, the displacement of the spring, the amount that the spring or elastic is stretched or compressed. Now, the force, we say, is K times X, right? So that becomes K times X times X. Wait a second, that's just KX squared, not 1/2 KX squared. So where's the flaw here? Where's the mistake? The force is changing. This F that we have to sub in here is not a constant force. It ranges from 0 to F, from 0 to the max force. The average force, which is really what we care about right here, the average force is 1/2 of the maximum force. So we go from 0 force to a force of F, the average force is 1/2 of that. 0 plus F divided by 2 is 1/2. So we're going to say it's 1/2 of F max times X. But F is going to be K times X. So it's going to be 1/2 of K times X, which is 1/2 of KX squared. Does that make sense? You don't have to derive it. You're not going to be responsible for that when it does. I answer that because the question was asked. Yep.
So does that also mean that as you pull a spring out gradually, that the force increases not exponentially but steadily?
That's correct. Yep. Yes, the question was, if you didn't hear that, as you pull a spring out, the force does not, is it correct to say that the force does not increase exponentially, but that it increases steadily? Absolutely. It increases steadily. And that's why we say F is equal to K times X. F and X are linearly related to one another. So as you double the distance, you're not doing anything exponential with F. When you double the distance, you're doubling the force. That is the definition of simple harmonic motion. As X triples, F triples. As X goes up by a factor of 37, F goes up by a factor of 37. The linear relationship, not an exponential relationship. Okay, good. It's a good question. And I'll tell you, when you go through these things, it does lead to a good understanding of things, but just know that you're not responsible for any kind of derivation like we just did there. Okay? I'll always answer those questions, or almost always answer those questions, but I'll also tell you if you don't have to know it to the test, which you don't have to know that. When it comes down to it, you got to know the kinetic energy of an object on the end of a spring is 1/2 mv squared, and its potential energy is 1/2 kx squared. Now, let's take a look at that little diagram we have of that spring vibrating back and forth again for a second here. You see this sentence that says the potential energy is related to the displacement of the spring. Of course it is. The equation is 1/2 kx squared. Right now, the potential energy of this spring is 0. When I stretch it a little bit, x is bigger. The potential energy is bigger. As I stretch it more, the potential energy is even bigger. When I stretch it this far, the force increases linearly with the displacement. But when I stretch it this far, the potential energy increases exponentially with the displacement. So if I double the length of it, the force doubles. If I double the length of it, the potential energy goes up by a factor of 4. Sorry, get this going here. All right, so I pull it out, force is bigger, the potential energy is bigger. If I pull it out, the force is even bigger, but now the potential energy is way bigger. I pull it out a little bit more, the force is bigger. The potential energy is way, 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 way bigger at this point. Now, because the potential energy is so big, when I let it go, it starts gaining a lot of speed. It goes back here, speeds up, gets to this point where it's not stretched at all, x is 0, Now all of that potential energy has been converted to kinetic. And now, because it's got so much kinetic energy, it just keeps going through here, and develops more potential energy. And then the potential energy is converted to kinetic, which is converted back to potential, and then the potential is converted back to kinetic, maximum kinetic, zero potential, and then it's converted back to potential, and so on, and so on, and so on. Again, simple harmonic motion, motion that repeats itself. Okay, we can think of it in terms of forces, but we can also think of it in terms of the conversion of energy from potential to kinetic. Now, I want to do an example question. In fact, I want to do two example questions, and then we'll leave it at that. I won't leave you with any homework tonight. We'll work on those questions in class tomorrow, since you guys, we don't have our test today. This one says a force of 8 newtons stretches a spring 10 centimeters. What's the spring potential energy stored in the spring? Here's my force. The spring is stretched 10.0 centimeters. We're going to make that 0.100 meters, and we want to find the potential energy here. The potential energy. We're going to say EP is equal to 1/2 kx squared. Perfect. So many numbers, except I don't know what k is. The good news is I know that k can be found by using F is equal to k times x. K is equal to F over x, which is 8 newtons divided by 0.100 meters. Why am I using kx rather than negative kx? Because negative kx is for the restoring force that pulls it back. Kx is for the force that I pulled it with, the applied force. I told you yesterday, though, if you get those two mixed up, don't panic about that. I'm not going to take off a mark for that. 8 divided by 0.1 is 80 newtons per meter. Now we're going to take that and sub it back into here. Say 1/2 of 80 times 0.1 squared. Let's figure that out. 0.5 times 80 times 0.1 squared gives me 400, which is, to 3 digits, just 400. No, that's not right. Oh, what have I done there? -1. 0.5 times 80 times 0.1 squared gives me 0.4. That sounds better. 400 is a really, really big number. For this, 0.4 sounds much better. All right, that's pretty straightforward, right? Couple steps, though. Not trivial, but not bad either. If I gave you this on day 2 of Physics 20, you'd be like, what? But now, like, our brains have developed enough by now that we can do this question.
That's in joules, right?
Yes, it is in joules. Yep. One more example. Example number 4, a spring with a spring constant of 10 newtons per meter is stretched and then released. How fast is the object on the end of the spring moving when it's released? Ooh. So picture this, you pull the spring, stretch it, and then you let it go, and then it speeds up. Is that not kind of like, just think about that for a second, is that not kind of like raise a car to the top of a hill, let it go, and it speeds up? Stretch a spring, give it potential energy, pull a car up to the top of the hill, give it potential energy, let the car go and it speeds up. Let the mass on the end of the spring go and it speeds up. It's almost exactly the same thing. We would analyze this question by saying EI equals EF. We would say the initial energy of this car is mgh. And the final energy when it reaches the bottom of the hill would be 1/2 mv squared. You guys recognize this? Remember this? 2 units ago? Well, when we're talking about pulling this spring back, stretching the spring, giving it potential energy, and then letting it go, we're converting potential to kinetic energy again, just like we were with the car going down the hill. But this time the potential energy that the object on the end of the spring had isn't mgh, it's 1/2 kx squared. So the car at the top of the hill has mgh potential energy. The stretched spring has 1/2 kx squared potential energy. Now, when the car gets to the bottom of the hill, it has kinetic energy, 1/2 mv squared. When the spring gets back to that fixed position or that equilibrium position, it has all kinetic energy. It's like it's at the bottom of a hill. So we're going to say it ends up going to kinetic energy, 1/2 mv squared. It's the same question, except mgh gets replaced by 1/2 kx squared. Now we cannot cancel out mass here because it does not appear in every term, but 1/2 does. You don't have to cancel that out, but you can because it appears in both terms. If I do, that leaves me with 10 newtons per meter times 0.25 squared. Mass is 1.0 kilograms times v squared. Let's get the number on the left side, 10 times 0.25. And then let's divide that by 1, although divide it by 1, you're just going to get the same number, 0.625. And then we're going to square root that. 0.79, Vf is 0.79 meters per second. So when you take the car up to the top of the hill and you let it go, it has a speed of whatever when it gets to the bottom of the hill. When you pull back the spring and then you let it go, when it goes through that fixed position, it has a speed of 0.79 meters per second. It's like it's at the bottom of the hill, because at that point, all of the potential energy is converted back to kinetic energy.